All right, if you're getting ready for a data science role, you already know the statistics interview is, well, it's the big one. It's that moment where all the theory you learned hits the real-world pressure cooker. And yeah, how you explain something like hypothesis testing can absolutely make or break your chances. But don't sweat it. Today we're going to break down the toughest parts and turn that pressure into total confidence.
And that really gets to the heart of the matter, doesn't it? There is a huge difference between just knowing a definition from a textbook and actually explaining it clearly to an interviewer. Because they're not looking for a robot. They want to see how you think, how you communicate, and most importantly, how you connect these ideas to solve actual problems.
So here's our game plan. We'll kick off with the interview hurdle itself. Then we'll build up from the foundational concepts, get into the art of testing, learn how to dodge some common modeling traps, and we'll wrap it all up with a winning framework you can use for pretty much any question they throw your way.
Exactly. So let's agree to forget about just reciting definitions. An interviewer is really testing your intuition. They're looking for that little spark, that moment where you take an abstract idea and, just like that, apply it to a business problem right there on the spot. That's the real skill we are honing today.
Okay, let's dive into the absolute bedrock of statistics. Seriously, if you get these two pillars right, everything else we talk about today is going to click into place so much more easily. First up, a real classic, descriptive versus inferential statistics. Interviewers love to ask this to see if you grasp the entire point of data analysis. So descriptive statistics, that's the easy part. It's just summarizing the data you already have. Think mean, median, a bar chart of last quarter's sales. It's all about what happened. Now, inferential statistics, that's where the magic happens. This is where you take a small piece of data, a sample, and use it to make an educated guess, an inference, about a much larger group. So for example, calculating the average salary of the 100 people you surveyed, that's descriptive. But using that sample to estimate the average salary for all 10,000 employees in the company, that is inferential, and that's where the real business value is.
So how in the world can we make that huge leap from a tiny sample to a whole population and feel good about it? Well, the magic wand we get to wave is called the Central Limit Theorem, or CLT. And what's so incredible about this is that your original population data could be shaped like anything. It could be totally weird and skewed. But if you go in and take enough decent-sized samples from it, and then you plot the average of each of those samples, the distribution of those averages will start to form a perfect, beautiful, normal bell curve. This theorem is the foundation for almost all of hypothesis testing because it's what allows us to make reliable predictions about everyone, even when we've only talked to a few. Okay, so the CLT gives us the superpower to test our ideas. So now we're moving into the art of testing, where we use data to make decisions, even when we're dealing with uncertainty. This is where you really start to shine as an analyst.
The p-value. Probably the most famous and most misunderstood concept in all of statistics. Let's make this super simple. A p-value answers just one question. If my initial hunch is true, how surprising is the data I just collected? So let's say you're running an A/B test. Your initial hunch, the null hypothesis, is that your new website design has zero effect. If you get a tiny p-value, like 0.01, that means your results are really surprising. There's only a 1% chance you'd see data this extreme if the new design actually did nothing. And that gives you strong evidence to say, you know what, I'm rejecting my initial hunch. The new design probably works. Now here's the #1 trap. A p-value is not the probability that your hunch is true or false. It's the probability of your data. If you can nail that one distinction, you are way ahead of the curve.
Now, anytime we use a p-value to make a call, we're taking a risk, right? We could be wrong. And that leads us to the two specific ways we can mess up. A type 1 error, which is a false positive, and a type 2 error, a false negative. And honestly, this medical test analogy just makes it impossible to forget. A type 1 error, a false positive, is like a doctor telling a perfectly healthy person that they're sick. It causes a ton of unnecessary panic and treatment. A type 2 error, a false negative, is telling a sick person that they're perfectly healthy. That's a misdiagnosis, and the consequences could be devastating. Now think about that in a business. A type 1 error might be launching a new feature that doesn't actually work, wasting a ton of money. But a type 2 error could be even worse. It could mean you miss out on a billion-dollar idea because your tests just failed to see its potential. Understanding this trade-off is absolutely crucial. So if p-values tell us whether an effect is real, confidence intervals tell us how big that effect might be. Instead of giving a single number like the average user clicks 3.5 times, it gives us a much more practical range, something like we're 95% confident the true average number of clicks is somewhere between 2.8 and 4.2.
When you're talking to a manager, this is just a much more honest and useful way to present your findings. It's not just a number, it's a number with a built-in measure of our own uncertainty.
All right, we've got our tools for testing. Now let's talk about building models and the sneaky traps interviewers love to set to test your real-world instincts. These are the kinds of questions that really separate the rookies from the pros.
This is probably the single most important distinction in all of data analysis, and getting them mixed up is the fastest way to derail a project and, frankly, lose all your credibility. Correlation just means two things move together. They have a relationship. Causation means a change in one thing is directly causing the change in the other. And here is the classic example that makes it so clear. If you actually plot the data, you'll see this amazing, strong correlation between how much ice cream is sold and the number of drowning deaths. So, should we ban ice cream to save lives? Of course not, because we're smart enough to know there's probably a hidden factor here.
And that hidden factor has a name. It's called a confounding variable. In this case, it's the summer heat, right? When it gets hot, more people buy ice cream, and when it gets hot, more people go swimming, which, tragically, leads to more drownings. The heat is causing both things to happen. The ice cream and the drownings are just correlated. Your job as an analyst and your answer in the interview is to always be on the lookout for the confounder.
And finally, a big interview favorite, linear regression. It's an awesome tool, but its predictions are only trustworthy if these key assumptions hold true. Now, instead of just listing them off, let's talk about what they actually mean. Linearity, for example, is the most basic one. Your model only works if the relationship you're modeling is, a straight line. And no multicollinearity is a huge one. It just means you can't have two input variables that are basically telling you the exact same thing, like having a person's height in inches and their height in centimeters in the same model. Including both just confuses everything. If you violate any of these, as you can see, your model's results can become completely unreliable.
Okay, so we've covered a ton of technical concepts, but remember what we said at the beginning? Passing the interview is all about communication. So let's finish up with the secret sauce, a simple, powerful framework for structuring every single answer you give.
No matter what they ask you, p-value, CLT, correlation, just follow these 4 steps. 1. Start with a clear, simple definition. 2. Immediately give a relatable real-world example, like the medical tests or the ice cream. 3, and this is the most important one, explain why it matters for the business. How does this help make money, save money, or avoid risk? And 4, show that you think a step ahead by mentioning potential pitfalls or what you might test next. This structure proves you don't just know the what, you know the so what, the why, and the what's next. It's an unbeatable approach.
Because at the end of the day, that's what this is really all about. An interviewer isn't looking for a human calculator. They're looking for a storyteller. They want someone who can look at the raw data, respect the uncertainty, and then pull out and communicate the clear, compelling story that's hiding in the numbers. The only real question left is, can you be the one to tell it?